This video is on a variation of covalent bonding called polar covalent bonds. What we've seen so far is that chemical bonds result from the attractions between opposite charges. The type of bond is determined largely by the electronegativities of the atoms that are being bonded together. When we consider electronegativities, remember it's just a numeric scale that represents an atom's attraction for electrons. Fluorine is the most electronegative element on the planet with an electronegativity of about 4.0. The least electronegative are in the opposite corner of the periodic table. Cesium and francium have an electronegativity of about 0.7. Ionic bonding happens when you have two atoms of drastically different electronegativities. Chlorine has a high electronegativity. It has a strong attraction for electrons. Sodium has a very low electronegativity. It has a weak attraction for electrons. So in this case, chlorine takes the electron away from the sodium. The result then is a sodium cation and a chloride anion. Of course, the sodium and chloride anion, cations and anions then join together. The opposite charges are attracted to each other and they form a ionic crystal. In covalent bonding, now we have two atoms that both have a strong attraction for electrons. In this case, I use two chlorine atoms. And so they both want one more electron, and they both have a strong attraction. And what happens is these atoms get pulled together, pulled together, pulled together, until they overlap and share two electrons between them. Another way of representing that would be show our dot diagrams, our Lewis structures, and you can think of the two chlorine atoms coming together to share a pair of electrons. The way we would usually represent that then is with a dash between them, showing the shared pair of electrons. In metallic bonding, all the atoms have a low electronegativity. They all have a fairly weak attraction for electrons, and so these electrons are free to just flow throughout the metal. They're not locked up in place. It's still the attraction between the positive and negative charges that hold it all together, and it's still a pretty strong bond, but it's very different than what we've seen in ionic and covalent. So let's consider electronegativity difference as it applies just to ionic and covalent. What we really need to think is that ionic and covalent represent different extremes. If the difference between two atoms is zero, that would be if we're bonding two atoms of the same element, that's 100% covalent. There's a pure sharing of electrons in between. As the difference becomes greater and greater between the two atoms, we get to ionic. And if we had a difference of 4.0, it would be 100% ionic. If we actually consider the numbers on the electronegativities, no atom has zero attraction for electrons, so you'll never get a difference of 4.0. So 100% ionic really is out of the question. So how do we draw our lines? Well, essentially, we're going to draw a line at 2.0, and we're going to consider anything 2.0 and greater, an electronegativity difference of 2.0 and greater, to be an ionic bond. Anything with a difference less than 2.0 is going to be a covalent bond. Let's go back and consider our example of chlorine again. We've got two chlorine atoms with a single bond between them. If we look at the electronegativity of chlorine, it's at 3.0. So the first chlorine atom has an electronegativity of 3.0. The second one has an electronegativity of 3.0. If we subtract to find the difference, we find out, well, that's a difference of 0. That is what we call a 100% covalent bond. In that case, we'd expect the shared pair of electrons to be distributed equally between these two atoms. Looking at a second example, here's hydrogen bonded to a chlorine. One hydrogen, one chlorine, one single bond. looking at the electronegativities, we see that hydrogen is a 2.1, chlorine is 3.0. So consider hydrogen at 2.1, chlorine at 3.0. If we subtract them, we get a 0.9, a difference of 0.9. Some of you are looking at my math and saying, isn't that a negative 0.9? But really what we just want is the difference between them. So think of it as an absolute value, difference of 0.9. Now, that certainly falls in the range of what we considered covalent, right? Anything with an electronegativity difference less than 2.0 was covalent. But you can see it's not going to be equal. Chlorine has a stronger attraction for electrons than hydrogen. So if you think about how the electrons are arranged, the electrons are being drawn more to the chlorine than the hydrogen. That's going to leave the chlorine with a partial negative charge. That's going to leave the hydrogen with a partial positive charge. A partial charge is designated with a lowercase Greek letter delta. That's what this little symbol here is. So when a molecule or when a bond has oppositely charged ends, the word we use to describe that is polar. A pole has two ends. In this case, polar bonds have a positive end and a negative end. So if we look at our electronegativity difference diagram again, we're going to further separate this. We still have our ionic end, that's anything with a difference of 2.0 or greater. But on our covalent end, we're going to divide it into two regions. We know that if the difference was 0, that's 100% covalent. If the difference were really small, a difference of 0.1, 0.2, 0.3, even up to 0.4, essentially we still say, well, those atoms are almost equal in their pull for electrons, their attraction for electrons. And what we do is we call that nonpolar covalent. Between that 0.4 and 2.0, we call those polar covalent. They're still sharing electrons, but it's an unequal sharing, and so there's a positive and a negative end. A polar covalent bond is a bond in which there is an unequal sharing of electrons between two atoms. Here's another diagram or chart that breaks it down even a little bit further. From a difference of 0 to 0.4, we say it's nonpolar covalent. If it's a little bit beyond that, we might say it's moderately polar. Get beyond from about 1 to 2 for a difference, we say it's very polar. And the extreme in polar is where we consider it ionic. Anything above a difference of 2, we consider that one atom has essentially taken the electron away from the other. Let's look through one more example. Here's a water molecule. We have two hydrogen atoms single bonded to an oxygen. If we consider electronegativities, we see that hydrogen is a 2.1, oxygen is a 3.5. Come back to our diagram. Here's oxygen with 3.5. I'm just going to consider this bond right here. Now, I know sometimes students will look at this and say, well, but there's two hydrogens. But if you look at how they're bonded, it's still just this oxygen is bonded to this hydrogen. That's what I'm looking at right now. Oxygen's at 3.5, the hydrogen's at 2.1. If I subtract, I get a difference of 1.4. Now, on our diagram, that was definitely polar covalent. In fact, that's very polar. So if we consider how the electrons are distributed, we know that oxygen is pulling the electrons a lot more strongly than the hydrogen. So the oxygen is going to end up with a partial negative, and the hydrogen is going to end up with a partial positive. Now, if we wanted, we could have considered this other bond instead. And again, oxygen would have been a 3.5, hydrogen a 2.1, difference of 1.4. This is also a polar covalent bond. And so the electrons here would have been shared also towards the oxygen, away from the hydrogen, leaving the oxygen with a partial negative, and hydrogen with a partial positive. This is how we make polar bonds. Anytime one atom has a greater attraction for electrons than the other, we get a bond that has oppositely charged ends. The word that's applied is polar. Thanks for watching. In my next video, we're going to try to look at how polar bonds come together to form polar molecules.